So as Vaughn said, we have Michael Peck, originally from California. He now works at Aurora Flight Sciences out of Cambridge, Massachusetts. There he works on developing loads models, analysis methods, and sizing criteria across full vehicle configurations and on multiple prototype vehicles, and that's what he'll be discussing today, doing that work on his latest program.
Thanks, Justin. Hi, everyone. My name is Michael Peck, and yes, I'm with Aurora Flight Sciences, and I'm going to be covering our approach to analysis and GFEM management with the HyperX Enterprise. So I'm going to be going over some of the HyperX capabilities that we've leveraged here and what the architecture relates to, especially in regards to program requirements. I'm going to outline some use case with our DARPA Liberty Lifter program. We've used HyperX in a varying number of programs with Hypersizer as well. But the Liberty Lifter program is a DARPA program that is a cargo plane designed for wing and ground effect. It's a full seaplane, so no landing gear involved here. And there's a goal to efficiently fly in high sea states, but also leverage low-cost manufacturing techniques and really trying to leverage information from the maritime industry and the wind turbine industry that uses more low-cost processing, even at the maybe the effective performance, but really focused on cost parameters as well as obviously weight. I'm going to be covering some effective guide rails to help flow information, not just down from the program requirement levels, but back up to once the sizing work is actually being done and how that gets and influences the downstream effects. So a lot of requirements go into the sizing of a vehicle. For something like a prototype program, it's not always as defined as well as a CFR type requirement that you have set out, and you have to kind of piece these together, and they're constantly maturing as you go through a program. So on the operational side, we have things that we pull from, whether it's CFR standards, military handbooks, joint spec operations, or other types of sources of data. And then on top of that, you have manufacturing tooling requirements. Idea of building a seaplane, considerations of things like using shipyards as manufacturing sites as opposed to traditional aerospace facilities can really drive what your tooling capabilities are. That will ultimately lead to sizing and analysis considerations that you have to take into effect as you're performing the analysis. So whether it's the high-level operational and manufacturing requirements, you're crossed with really working with other teams in the product development side to flow in information from flight physics, your ground load considerations, environmental factors and operations, fatigue cycling, as we've heard from other things, aeroelastic stiffness requirements, penetrations that come down the line when you don't want them, and obviously, ultimately, the testing requirements that you need to facilitate for static proof loading, fatigue loading, or even vibration testing. Something like Liberty Lifter that doesn't have landing gears, you need to start thinking about how you're going to cradle this thing if we need to start getting vibration testing going on or other factors. So when a stress analyst is going through, there's been a lot of great topics of what kind of whether stress analysts become kind of data managers as we go through and have to pull information from a lot of different sources. So from a loads perspective, we have loads from external load sets or reports, internal loads models, miscellaneous interface documents for payloads, cargoes, pylons, and any criteria that you have set for what your requirements are driving for your program. When you're using novel materials, sometimes you don't have your full material allowable sets like you have from an OEM on your startup, and you're constantly inputting new and injecting new data as you go through. So whether it's a reference document, shared drives that you're pulling from, public data sheets that are available, you have to really manage where that comes from. And as a stress analyst, that becomes, can become dangerous or at least cumbersome at the least. On the design space here, we have things like ply laminate families, people's experience, whether they're really composites based, knowing how ply drop-offs manage families, symmetric balance systems to leverage, or just industry standards that you want to set for whatever your program requirements are. And on the analysis method, this is where the stress analysts become really the controllers of, and you hopefully have some type of stress criteria document that you're starting out with, maybe some program OEM standard methods that you're going through, or if you're needing to leverage public data sets, you're using a mix-mash of tools and spreadsheets that have been created over time, and whatever various FEA packages you have available at your company. And so whether the stress analyst is responsible for controlling all that information and being consistent across the teams and making sure that somebody working on a wing section isn't totally off target with what the person on the fuselage side is doing based off of where you're at in your program. Within the HyperX enterprise, you can utilize that HyperX database to help manage a lot of these sets and keep a consistent flow as you're starting from the top down and spreading out to your contributors. So for Liberty Lifter, for example, we're able to generate FEA loads that's controlled within the database and apply any local pressures, temperatures, and factors that are relevant to specific areas, as well as what filtering criteria that we want to apply on different sets of the program. For material allowables, the material library can be set, whether it's controlled in an Excel document that's readable with the database or in the database directly. Those things are preset and managed and has traceability across the different design cycles. Additionally, the laminate families here can be preset to match what test data is available and can be matured upon as you progress through the design and set some type of bounds to kind of give analysts a place to work through, but not having to be uncertain with what data they have available to work with. Additionally, we have environmental knockdowns and features set in that space. With along stock sizes for things like core materials, your manufacturing limits that you have set based off of your facilities, stiffness criteria, minimum gauges, and with the analysis methods, going through and setting what applicable methods or plugins that you want to use for your approach. I think this is the one that I think always gets me is when you get a load set, you're asking yourself, unless it's really well documented, are these ultimate loads here? Are these limit loads? I think a lot of people have been in that case, and you're wondering whether you're throwing a factor there or not. And having a traceability on what those loads go through is, I think, a really helpful set for especially handing off somebody coming on board to the program and not having to dig through and be hoping and fingers crossing that somebody put a note file in the comments. Same with margin requirements as you go through prototyping. These things are not static as you are working through this process. On environmental cases too, you might find out that, hey, now we're not flying at 180 anymore. We're going to go to this new set here. So now these are loaded in this HyperX database. I'm going to go through some more detail on how this was used in Liberty Lifter. So here we have a standard CFR document for how VN diagrams are laid out for your load cases. But for Liberty Lifter here, we also have to consider something like a whole main landing float. So still a CFR regulation, but a new case that's maybe not relevant to the entire section. So here you have a step landing case, and I learned a lot about boats on this program, and that's the transition point for the hydrodynamics area. A lot of boat terminologies. I think outside of HyperX, just learning how to talk to boat people is also a skill that is that's still a work in progress, but always learning. And then balance during cases for when your seaplane is coming into a wave or landing maybe closer to the tail. So these factors really play into what the requirements are on your vehicle. Now, the design load sets that come into that HyperX database that tie into your loads help manage this. So for our flight maneuvering cases, that might be applicable to our entire vehicle that's experiencing bending in flight for up bending or down bending cases. But something like a specific CFR for hydro landing cases may only be relevant to the bottom section of the vehicle. And so that's where things like design load overrides can help specify what parameters are used where. Other things like external tools and scripting can help also down select through your criteria reports, any potato plots that you get along the process, and any shear moment diagrams to help really control what material is there and leverage smart sizing techniques to reduce processing time in that. On the material allowable side, Like I said, trying to use maritime materials, so that includes foam cores, glass fabrics, and resin-infused systems, which are things used in aerospace, but not necessarily on primary structures or in a wide-scale approach. And Liberty Lifter being a large cargo plane, we're using a lot of these materials, and so that's where you really need to have a good control of what those allowables are and how you're considering them. So managing that at a global level ensures that people aren't going through and creating their own spreadsheets or making assumptions on what's B basis, what's A basis that we need to apply, and what are their stock sizes. Can we actually get, do we have any foam core thickness at our disposal, or are tooling constraints really limited to what stock sizes we have on hand or can machine at a low cost? Environmental factors also play a role here to help set the bounds for sizing and what your test data is as you go through. And you can make program level decisions on where you want to cut off things to make conservative or appropriate decisions at the stage of your analysis. Kind of a use case here on, it's really great to set parameters at the top level, but one of the concerns I think at the individual contributor level is, hey, I'm bound now by what you gave me. Am I not able to do my job because I now only have this one material here when I really need to look at some other options? And here we have an example of a trade study that was done where our baseline material was a Rocell R71 foam core density, and that was handed down to do sizing for some panels. And one of the critical failure modes was a buckling failure mode, where our transverse shear factor plays a huge role for a sandwich panel in knocking down what our buckling capability is. So when you have a lower loaded panel, so we have load over density here, at lower loads, you have some trade-off on where your R71 is more efficient in thicker cores, but at a certain point, you can show that the higher density core is a more efficient material. Now, this is going through the knockdown and D matrix classifications, but updating those material properties at the lowest level from a contributor can then flow back up, and then you can make program-wide changes that can then be re-rolled within the enterprise and maintain for consistency. So once you've made the decision to update your materials, everybody on the team can then leverage that on the next cycle as you go through the process. On the design space, we have manufacturing requirements, same kind of outlines depending on people's experience or what they're aware of. You might want to set bounds on what your ply families can be, any layup patterns that you want to establish, criteria that can be, again, flowed down at a GFEM level and still maintain as you break those things up between structures on the vehicle. One of the key features, which I'll be showing in more detail, is the idea that you can flag these features. So when somebody does add a new design parameter that maybe exceeds where you're at, you have the capability to track that and make sure that it's the right change for the program and meets the requirements that you've set. And as we talked about, and I'm excited to hear more, is the stiffness requirements that can be really critical for aeroelastic considerations. So here we have the horizontal tail box on the structure, pretty simple structural layout, but you have section cuts here to ensure that your bounds are met. So if you have some type of stiffness criteria to meet your aeroelastic margins, you have a bound to set on a minimum side and a way to track that as you go through the iteration process. You can easily pull this out and tabulate this and have a history, and it makes flight physics people really happy when you give them that information ahead of time, as opposed to just dropping them a bunch of properties down the load and finding out, hey, our stiffness just came out of whack, and we're going to have to go back and you're going to add more mass. So it really makes a friendly interface when working between teams. On the analysis side, this is where I think a lot of people are hesitant to totally give way to setting parameters ahead of time. But by defining failure modes with either the native HyperX analysis IDs or any specific plugins that you want to build for your specific use case, you can document what modes are being used on your program, and you can ensure that anything that's being written to a margin is conforming with your criteria and your program requirements that you have met, whether it's in your stretch criteria or higher level program tracking. when you're going through a prototype vehicle, a lot of things are changing, whether your margin maturity or your testing maturity, your loads maturity, your configuration maturity, and that can also affect what margin you need to hold at a different phase. And so being able to constrain that and specifying what those parameters are, as well as adding new cases that might be more representative as the configuration is maturing, is a really helpful aspect in managing the database. So as we go through, here's a standard phase, whether it's conceptual design to preliminary design, or if you're in the later stages of manufacturing. A lot of times, hopefully you have your material levels. A lot of times those things are, like I said, being injected through the program as you mature your configuration and your design. But the layout's maturing, and we end up at the bottom side of this on the sizing here. And we have a lot of things that ideally waterfall into each other, and a lot of times they're lagging, and you're getting things last minute, and you're trying to, as much as you can condense those gaps between and react to those changes, makes a huge difference. So program driving requirements that size the materials that you're selecting, the configurations that you're using, and the external loads that you're generating are going to be a major factor into that final sizing loop that you're going through at the end. Now, when you get to the, for example, breaking out wing, fuselage, empennage to each other, they might not be aligned at the same time, but you still need to reintegrate that in before you go to the next configuration change and go through our process. So as our wing, is more focused on, we're ahead of the game, but maybe at the phase B, our fuselage needs a lot more work, and so we're holding on before we reintegrate into our internal loads model to reprocess through these steps. So the sizing and stiffness changes that you can maintain within each section really help keep consistency and traceability to where the sources of information are coming from at the high level, and to where you're not having to miscommunicate from teams, and you are always starting off at a similar point within the enterprise, and then reassessing as you keep in that control. From the GFEM side, I think this is where HyperX really integrates well in terms of automating a lot of these steps, whether it's property management or just the sizing details or allowables, where using like a typical include file structure here, you can use HyperFEA to just kind of target what section of the vehicle you're working on and keep that traceability of stiffness in that local region, as opposed to having to worry too much before you reintegrate, but still starting from that consistent standpoint and where you're going. The way that we manage this on Liberty Lifter is having a GFEM integrator. It's in charge of managing the internal loads model, setting those boundaries and breaking up the pieces, and establishing the global settings that are used across databases. And then they're also responsible for collecting that at the end. The subsection leads are the ones that are going to be deciding what parameters how their pieces are broken up and actually sized by each contributor, and what actual more specific aspects. So where do we need to apply fuselage pressure for a landing case? What are our wingtips doing here? Do we need to carry that onto the tail? That's where the subsection leads are doing, and they're usually the ones that are reviewing the actual work that's being done and making sure that everything's conforming to the program requirements. And at the individual contributor level or the stress analyst that's doing the sizing, they I think everyone likes to have as much data as they can accessible to them, but they also don't want to be over constrained by what is present. They have to have some ability to make decisions and make good choices that represents their structure well, and flow that back up. And that's where I think the enterprise comes into a real use case, is by having the individual contributor do the detail work, and then have the traceability as you go back up and down this process. So this is where the kind of idea of guide rails versus constraints come into play. And it's up to really good communication from a GFEM integrator and subsection leads to set the responsibilities of setting those bounds, but allowing the contributors to push it where necessary. So here at the bottom is kind of where you can see those pending changes report, where as you break up a parent database into a child database, and we've also used grandchildren databases even, to really keep the family tree going. And we have, so that's a fantastic use case, but the worry is, okay, that you've done that, now how do you know if anyone changes? And that's where these change reports come into play to help flag all of those things to make sure at the higher levels you're really keeping in charge with that. There's a lot of things to consider there in terms of what stage of the project are we at. Prototypes move fast. You really have to be agile, and you're going through iterations. You have to be mistakes are gonna happen. You have to be able to make adjustments quickly, and so being able to make those changes, communicate to the teams. How are the teams split up? I think usually you'll have your section IPTs groups. Even then, they'll be integrated with other groups that are driving, testing, driving subsystems, and those things really come into play with making those local decisions for where you're at, and understanding what is common and what is unique to where you're doing. Are we doing sandwich panels on the wing? Are we doing sandwich panels on the fuselage? Are we going to a stringer-based design? And how does that tie in from a holistic approach of analysis? And then, you do have to take the reality of what is the size of your cases. For a GFEM, are we talking about a 30,000 element or grid GFEM? Are we talking about 100,000 grid GFEM? And how many load cases? I think we all want, if you ask some older stress engineers, like 10 load cases and your size in a wing. Some people say, no, 2,000 load cases. I think there's a happy medium, and using some of these, critical down selection tools on top of your classic shear moment diagrams and potato plots really help you bridge what's a smart way to approach loads processing and the sizing. I think ideally at the end of the process, you want to go through and do the detailed churning of all the analysis, but there's just, there's not a reality in which that's a smart play in the sizing steps. I think there's also a lot of room for improvement on this tool to help kind of mature some of the capabilities there. There's some substructuring requirements. So, if you're starting with a GFEM, there are times where you do need to go to a more detailed FEM appropriation. But I think you can still use traceability between analysis IDs and scripting to help tie these things in together and maintain those traceabilities across databases and models. And automating some of that with scripting or other plugins can be really useful. Maintaining those analysis methods is really, like I said, there's a lot of great tools with Excel spreadsheets, and sometimes maintaining that across databases and can be helpful as well. Additional use for monitor points and grid point force balancing would also be a great way to track some of these changes for loads. I think that the ability to add non-FEA capabilities helps introduce some of those things, but making them more native to the HyperX enterprise would be a really useful feature. Additionally, documentation on project settings can also get into the weeds. There's a lot of tables in the project settings, and sometimes it takes a couple cups of coffee and some time to really dig through them and understand what knobs you're turning, and that making sure that that's communicated down the line. So when a user is in a certain project, they know what project settings are affecting the analysis that they're doing. And then finally, some of the flags that go into the child support do not get rolled back up, such as design load overrides and some other features that can get changed but do not get flagged on every integration. So it still takes really diligent engineers to understand what's being done inside of the enterprise database and thorough checking to go through this. But it's, I think, a leaps and bounds ahead of throwing something out on a shared drive and hoping that it gets reviewed. So that is my presentation. There's a message for IT support on here.
Oh, not now. No.
Hi, Michael. I was wondering how many folks you had working on these child databases at a time, and also
Track of who's talking.
it's me.
Oh,
sorry.
sorry.
In the middle. And then a second question, not really related, but you mentioned scripts and plugins a couple times, so I was just wondering how you managed those updates to those specifically across different team members.
The first question was about how many of the fleet?
Yeah, or how many like engineers did you have working on child databases in parallel?
On this program and other programs, it ranged. On a previous program, we had, I think, up to 12 or 13 people working on various sections. This one, we had fewer than, across the team, but it's, broken up to we've used a number of people. Mm-hmm. On the second question, from the script side, we mostly haven't gone too outside of the bounds of the pre-existing Collier scripts and tools. Anything that's been added there has just been kind of modifying the current file structure and scripts there. I think there's a lot of use down the road of using more of like a controlled repository to manage those. That would be great to implement.
Thank you.
Hey, Michael, first, thank you for providing that areas of growth slide. We love getting those, so thank you. My question was on that last slide. You said for the enterprise case for the child databases that it would be great if it got flagged for new design cases. But the design cases come from the initial FEM. Is this for if somebody makes like a combination case or?
Yes, correct. If you make any combination cases or if you do design load overrides, those do not get flagged back up on reintegration.
Got it. And then just because I have the mic, I have a curiosity question. For this kind of vehicle, are you seeing the critical design loads come more for like the water cases or wing and ground effect or flight cases?
Depends on the section of the vehicle. Bottom pressures are very high on this. Going in high sea states, large waves, they really slam into it. There's been, talking to boat people, they can get to hundreds of psi in certain areas, but it's depending on the vehicle and your approach, and the sea states can really flow into things.
Thank you.
I think the plane has a really interesting empennage design. I'm just curious if you could comment on what drove that kind of delta shape. On
the pie tail on the back. I believe it was to do with the cargo door, so you could open up the cargo door. I don't know if that's still in the design criteria, but it was to be able to get cargo in and out more efficiently.
How often are you
Sorry.
How often are you reintegrating into the GFEM and then rerunning for internal load distribution and then breaking it back out into the leads?
For the reintegration, it's a single per GFEM release. So we've gone through, depending on the loads drop, we've gone through multiple, up to 2 or 3 internal loads revisions within that. Sometimes if there's something that's specific to a certain region, we might not give the tail or update unless we need to. Or for example, or if there's local issues or local sizing. So, at most 2 or 3 times, hopefully, within a single loads drop.
Okay, thank you.
Can you go back to the artist rendering slide? How does it turn without dipping the wing in the water?
How does it turn?
Yeah, without dipping the wing in the water.
Well, so we have in this picture. There's some daggerlets there. I mean, you can impact the water, but it's not always flying around wing and ground effect. It has a 10,000-foot ceiling, so you can climb up. You're still not a pressurized vehicle, but you can climb up to a high altitude. It's not constantly flying at wing and ground.
Gotcha. Thanks.
All right. Well, thank you very much.